On the left, the world as it exists today, completely dependent on a single 33-kilometer strip of water. On the right, what $200 billion in 6 years of pure human defiance could actually build to make that dependency disappear forever. The question isn't whether it's possible. The question is whether anyone will actually have the nerve to finish it. Oil just hit $126 a barrel, the highest price in 4 years. And it didn't happen because of a war, a shortage, or a market crash. It happened because of one narrow gap of ocean that 20 million barrels of oil pass through every single day, 1/5 of everything the entire planet burns, ships, drives, and heats itself with, all squeezed through a bottleneck so vulnerable that a single block tanker can send shockwaves through every economy on Earth within hours. And it's not just oil. Fertilizer for half the world's farmland, the plastic in your phone case, the raw materials behind half the pharmaceuticals in your medicine cabinet, all of it, at some point, has to pass through this exact same stretch of water. I'm standing at Fujairah Port right now, the last safe harbor before ships commit to the strait, and behind me there are 180 fully loaded tankers sitting completely still, anchored, waiting, going absolutely nowhere. This is what global vulnerability actually looks like in real life. Not a headline, not a chart, just an ocean full of ships too afraid to move. Every single barrel that leaves Saudi Arabia, the UAE, Iraq, Kuwait, and Qatar has no choice but to exit through this one impossibly narrow gap. And for decades, the solution has existed only on paper, tucked away in engineering journals. Nobody wanted to fund because standing directly between the Persian Gulf and the open ocean is 32 kilometers of some of the most violent, unforgiving terrain on the entire planet, and removing it is exactly what this story is about. This mountain range is the only reason the bypass hasn't already been built. 2,087 meters of solid Hajar limestone rising straight out of the earth with no roads, no infrastructure, nothing but raw, hostile rock across the most rugged peninsula in the entire Arabian Gulf. And this isn't ordinary stone. Hajar limestone is hard, deeply fractured, riddled with hidden cavities that swallow drills without warning. The exact same rock that forms the sheer cliffs plunging straight down into the sea along this coastline. For comparison, the Panama Canal cuts through 77 kilometers of relatively flat, forgiving jungle. This bypasses less than half that distance, just 32 kilometers, but engineers who've studied both projects will tell you plainly that this one is roughly 10 times harder, because you're not moving through soft ground, you're removing an entire mountain range one blast at a time. When the survey teams first arrived, they discovered something immediately humbling. No road reached any of their survey points. Every single piece of equipment had to be flown in by helicopter, one load at a time, just to begin measuring a mountain nobody had ever seriously tried to cut through before. The survey alone consumed 2 years, and at 40 meters below the surface, drills hit something nobody expected, a cave system the size of a cathedral, hollowed out inside the mountain itself over millions of years, meaning the mountain wasn't just solid rock waiting to be blasted. It was hollow in places, unpredictable, and every single detonation sequence for the entire project would now have to be redesigned around a hidden underground cave network that could collapse without warning. Engineers deployed 3,000 seismic sensors across the entire mountain range, mapping every underground cavity with painstaking precision before a single blast was even planned. Because buried somewhere inside that same rock sat a freshwater lens, an underground reservoir the entire construction operation would eventually depend on to survive. Breach it accidentally during blasting and the canal floods before it's even finished being built. Engineers studied 3 possible routes through the mountains. The southern route ran 38 kilometers, longer but gentler. The northern route was shortest at 28 kilometers, but it cut directly through peaks rising over 2,000 meters, essentially unbuildable with existing technology. In the end, they chose the central route, 32 kilometers long, climbing to a peak elevation of 650 meters, requiring 3 separate lock systems, each 300 meters wide and 25 meters deep, to lift and lower ships across that elevation change. To carve this canal, engineers calculated they would need to remove 400 million cubic meters of solid rock, roughly 40 times the total excavation volume of the Panama Canal. A number so large, it's almost impossible to visualize until you understand that before a single blast could even begin on the actual canal, workers first had to carve 180 kilometers of access road directly out of vertical cliff faces, just to physically reach the construction zone. And that road didn't come easy. Workers drilled directly into the cliff. Controlled explosions sent chunks of the mountain crashing into the sea below, and what remained was a narrow ledge, just wide enough for a single truck to creep across, one blast at a time. After every detonation, workers cleared debris entirely by hand, because at this stage, no machine could safely reach these narrow, freshly blasted ledges. This is how roads are born inside vertical mountains, one dangerous meter at a time. Every piece of heavy equipment had to arrive by sea. Because there was simply no other option, each machine lifted ashore by crane onto a temporary jetty before being driven up gradients as steep as 45 degrees, crawling along ledges suspended directly above open ocean, where a single miscalculated turn meant a machine going straight over the edge into the water below. It took 6 full months just to carve 180 kilometers of mountain road before a single ton of actual canal excavation could even begin. And once the road was finished, an entirely new challenge emerged because 10,000 workers now needed water, food, shelter, and medical care in a location sitting 200 kilometers from the nearest city, meaning every piece of that infrastructure had to be built from absolutely nothing, on site, before construction of the canal itself could even start. With the nearest source of fresh water 200 kilometers away, workers built an entire desalination plant first, because nothing else on this project could proceed without water. The site also needed 200 megawatts of continuous power, and with no existing grid connection anywhere near this remote stretch of coastline, workers built an entire power station before they ever touched the mountain meant to become a canal. Only once the road, the water plant, and the power station were finished could the true construction army finally reach every single point along the 32-kilometer canal route. What came next was one of the most meticulously planned demolition operations in modern engineering history. The complete blast plan for this project ran 4,000 pages long, with every single cubic meter of rock assigned its own blast number, its own precise charge size, and its own detonation sequence. In total, the plan called for 40,000 individual controlled detonations, scheduled and mapped over a full 2 years before the very first charge was ever placed into the rock. Every cave discovered during the survey phase had to be filled with grout before the surrounding rock could be blasted, converting what had been an unstable, unpredictable underground void into something engineers could actually control. 800 vibration sensors were embedded directly into the mountain, monitoring every single blast in real time, and if ground movement ever exceeded safe limits, construction stopped immediately. No exceptions, no shortcuts. The very first blast was deliberately small, filmed by cameras running at 1,000 frames per second just to study exactly how this specific limestone fractured under pressure, feeding that data back into the models so the real, large-scale blasting could finally begin with confidence instead of guesswork. Even fragment size mattered enormously here. Rock chunks too large couldn't be lifted by the excavators. Fragments too small filled the canyon with suffocating dust clouds that could halt work for days at a time. Before the canal itself could be dug, engineers installed an underground cut-off wall specifically to protect that fragile freshwater lens the entire construction workforce still depended on to survive out here. Then, without warning, surveyors discovered an unstable slope sitting directly above the planned canal route, roughly 200,000 tons of fractured, unstable rock hanging precariously above where workers were scheduled to be standing. The entire route had to be shifted. 80 meters south, new surveys, new blast patterns. 4 days lost just from that single discovery, and it was only the first of many times the mountain itself would force the engineers to adapt on the fly. 40,000 blasts, every single one carefully sequenced in advance, and still the mountain had absolutely no idea what was coming for it. The very first production blast tore 50,000 tons of solid mountain apart in just 8 seconds. And in that single instant, the canal stopped being a plan on paper and started becoming something real. 40 excavators worked inside the cut simultaneously, loading 100-ton dump trucks every 90 seconds, essentially watching the mountain leave the site one truckload at a time. One truck rolled out roughly every 30 seconds, each one carrying 100 tons of what used to be solid rock, 24 hours a day, 7 days a week, without pause. Standing inside the canal itself during those early weeks, you're looking at walls that were still part of an intact mountain just 3 days earlier, and already the cut had reached 30 meters deep. Each blast face required 80 separate drill holes, each one 12 meters deep, adding up to 960 meters of total drilling for a single blast alone, a process workers repeated relentlessly, day after day after day. The explosive of choice was ANFO, a simple combination of ammonium nitrate and fuel oil, the cheapest explosive available that still breaks the maximum amount of rock, used at roughly 40 tons per blast, detonated using millisecond delay timing so precise that each individual hole fired just 17 milliseconds after the one before it, causing the rock to fragment cleanly and predictably instead of shattering chaotically in every direction. The dust cloud from a single blast alone could shut the entire site down for 6 hours, so crews deployed water cannons that suppressed it in roughly 20 minutes, allowing workers to move back in almost immediately. Blasting itself stopped at midnight every night, but the excavation never truly paused because the mountain kept moving day and night without rest. And with 400 million cubic meters of displaced rock needing somewhere to go, Engineers made a decision as practical as it was ambitious, dumping it directly into the sea, essentially building brand new coastal land using the exact same mountain they were tearing apart to create the canal. At 100 meters deep, the machines working at the bottom of the cut looked like toys from the rim above, tiny dots moving inside a canyon that workers were quite literally carving out of a living, breathing mountain range. At 120 meters down, the mountain began to bleed, groundwater seeping steadily through the fractured limestone walls, forcing crews to deploy pump trucks within the hour and eventually install a permanent dewatering network directly into the canal walls themselves, pumping away 50,000 liters of water every single hour just to keep the excavation dry enough to continue working. But the highest peak along the route, standing 650 meters tall, simply couldn't be blasted apart from above using conventional methods. So engineers brought in a tunnel boring machine instead, grinding through the hardest limestone in the entire Arabian region at a rate of roughly 8 meters per day, quietly chewing through the one section of mountain the open cut method could never reach. Behind the machine, a conveyor system hauled out the tunnel's spoil continuously, removing 3,500 tons of limestone for every single meter of tunnel completed. Then, one night, a wall section along the open cut turned unstable without warning, forcing the evacuation of 200 workers at 3 a.m. Engineers were on site by 4. By 8, that same morning, the slope had already been completely redesigned. This kind of speed wasn't luck, it was necessity, and it's why 180,000 rock bolts were eventually driven into the canyon walls, physically holding the mountain open against its own crushing internal pressure, followed by a layer of shotcrete sealing every surface, converting what had once been fractured, unstable rock into a stable, engineered structure that could actually be trusted. Financial markets noticed almost immediately. The moment the bypass officially broke ground, the so-called Hormuz risk premium built into global oil prices dropped by $8 a barrel overnight, meaning this canal was already saving the world money before a single ship had ever passed through it. By the time crews reached 16 kilometers of open cut, they'd hit the true midpoint, 200 million cubic meters of rock removed, with exactly 200 million more still waiting ahead of them. Then came one of the defining moments of the entire project. The tunnel boring machine finally broke through, meeting the open cut section for the very first time, connecting the full canal route from underground straight through to open air in a single continuous line. In the first completed section, workers reached full design depth, 25 meters below sea level, 300 meters wide, standing on what would eventually become the actual floor of the canal. Around this same time, shipping giant Maersk signed the very first transit contract for the still unfinished waterway, committing $50 billion in future shipping volume before the mountain had even finished being demolished, a staggering vote of confidence in a project that, on paper, still looked nearly impossible. Along the deepest sections, canyon walls rose 250 meters straight up, making the workers below look like ants. Against the sheer scale of what they were building, an entire mountain carved into a canyon in just 3 years. For comparison, the original Panama Canal took a full decade to dig. This project did it in 3. Eventually came the last major blast, marking the completion of the main excavation phase, 400 million cubic meters of rock removed in total, the entire canal route now clear from one sea to the other. Workers who had spent 3 straight years tearing apart a mountain finally stood together at the bottom of what they'd created and celebrated, because the hardest, most dangerous phase of the entire project was finally behind them. But an open trench through a mountain isn't a functioning canal, not yet. The freshly blasted rock face now became the outer form for a permanent concrete lining, and workers began installing the inner formwork, with concrete poured directly between the 2 layers to create walls strong enough to hold back the immense pressure of 25 meters of seawater constantly pushing outward against them. Massive rebar cages were installed to resist that force, every single bar placed by hand, slowly transforming the raw mountain wall, section by section, into permanent reinforced concrete, hiding the original blasted rock completely behind the smooth lining that would eventually touch the sea. That concrete was waterproofed from the outside in, using a membrane specifically designed to hold back the mountain's own groundwater, which was still pressing inward from outside the canal walls. The canal floor itself received a full meter of poured concrete, smooth to a finish, precise enough for massive supertankers to pass safely above it. Kilometer by kilometer, the transformation became undeniable. 2 full kilometers of finished canal already showing bright white concrete walls and a flawless, smooth floor, a literal mountain converted into a functioning waterway. Bollards, navigation lights, distance markers, every detail slowly turning raw concrete into an actual navigable shipping lane. Lining crews worked from both ends of the canal simultaneously, closing the gap kilometer by kilometer until the entire route could finally carry a ship from end to end. Inside the tunnel sections, specifically, engineers used precast concrete segments, the exact same lining method used in modern metro tunnel construction, just scaled up dramatically to accommodate ships instead of subway trains. In an engineering requirement no canal in history had ever needed before, the entire waterway was designed so it could be fully drained for maintenance within just 72 hours, using pump stations built directly into the canal walls themselves. With 32 kilometers of canal now fully lined, the waterway itself stood complete. What remained were the 3 lock systems, the mechanical heart of the entire project, responsible for lifting and lowering ships, weighing up to 300,000 tons across the mountain's 650-meter elevation change. The first lock basin alone stretched 400 meters long enough that the entire Eiffel Tower could be laid down lengthwise inside it with room to spare, and workers carved the entire structure directly out of solid rock at the canal's entrance. Each lock wall was engineered to hold back 400,000 cubic meters of water, and the rebar cage for a single wall alone weighed 8,000 tons, placed bar by hand, followed by the single largest concrete pour of the entire project, 15,000 cubic meters poured continuously over 60 straight hours. The lock gates themselves were fabricated all the way in South Korea, each one 65 meters wide, 30 meters tall, and weighing 3,000 tons, larger than any gate ever built for any canal in human history. These massive gate sections arrived by ship, far too enormous to transport by any road on Earth, craned directly off the vessel at the canal mouth before being guided into position by workers on the launching platform below. There was no crane on the planet large enough to simply lift a gate this size into place, so instead, engineers floated it in using powerful winches to pull it millimeter by millimeter into its exact seated position. A specialized hydraulic system, capable of moving 3,000 tons of steel against the full crushing pressure of the water, allowed these seemingly impossible gates to swing open and shut with precision. Rather than draining over the top of the gate, water moves through underground culverts built into the lock structure itself, allowing an entire chamber large enough for a supertanker to completely fill in just 12 minutes. A dedicated control building, built directly into the canal wall, houses the workers and computer systems responsible for managing every single cubic meter of water movement through the entire lock system. The second lock sits at the very peak of the canal's elevation profile, 650 meters above sea level, with walls rising 45 meters, representing the single highest engineering point of the entire project. The third and final lock completes the sequence, carrying ships from the Persian Gulf up and over the mountain, and safely back down into the Arabian Sea on the other side. 3 lock chambers, 1 mountain fully crossed. A supertanker enters at sea level on one side, rises the full 650 meters through all 3 lock systems, then descends again and exits directly into open ocean, completely, bypassing the Strait of Hormuz altogether. Inside these chambers, water rises at a rate of 3 meters per minute, meaning a lock chamber built to hold 3 years of relentless construction effort fills completely in just 12 minutes flat, a genuinely humbling contrast between how long something takes to build and how quickly it actually operates. But the canal still needed proper approach channels, dredged on both ends to be truly functional, requiring 15 kilometers of seabed excavated down to 28 meters depth on the Persian Gulf side alone, with all dredged material carefully deposited in a designated deep water disposal zone far from the shipping lanes. In total, 50 million cubic meters of seabed material had to be removed just to complete the approach channels properly. To protect both canal entrances from powerful ocean swells, workers constructed massive breakwaters using individual rock armor units weighing 15 tons apiece, placed one by one from specialized crane barges working along the coastline. Every single navigation buoy along the approach was positioned with centimeter-level accuracy, because supertanker captains would eventually be following this exact buoy line from as far as 50 kilometers out at sea. Meanwhile, teams of divers inspected every single meter of the underwater canal walls, verifying that everything workers had built above the waterline held up just as securely below it. Every functioning canal also needs a working port on each end, and crews built dedicated tug berths, fueling points, and control facilities specifically to operate this new waterway on a daily basis. A dedicated canal control tower was constructed with radar coverage extending 80 kilometers in every direction, giving controllers a complete real-time view of every single ship operating on either sea. 800 cameras were installed along the full 32-kilometer length of the canal, ensuring that every meter of what is now arguably the world's most strategically important waterway remains monitored continuously day and night without interruption. Engineers even installed a full traffic signal system specifically designed for supertankers, managing safe two-way traffic through a channel just 300 meters wide, an extraordinarily delicate balancing act given the size of the vessels involved. Recognizing the catastrophic risk a fire aboard a supertanker could pose inside such a confined space, workers built an entire dedicated emergency response infrastructure specifically to prevent any such incident from spiraling into a full-blown disaster. As construction wound down, crews methodically removed every last trace of the effort that had built this canal: the cranes, the temporary roads, the construction camps, leaving behind only the finished waterway itself, quiet and permanent where a mountain used to stand. Then came the full transit test, a single vessel guided completely through all three lock systems, experiencing the full 650-meter elevation change, exactly as engineers had calculated years earlier on paper, everything working precisely as designed. A permanent power station built directly into the mountain wall itself now houses the turbines expected to keep this entire canal system operational for the next 100 years. 8,000 workers, 30 different nationalities, all working side by side. 6 years of construction, 400 million cubic meters of mountain removed, a functioning 32-kilometer canal carved through. Solid rock where absolutely nothing existed before, complete with 3 full lock systems and 400 million cubic meters of displaced earth, reshaping the very coastline around it. What stands today is arguably the most strategically significant canal on the planet, finally complete. And then, quietly, without fanfare, the very last worker walked out of the site for good. The construction finally finished, an entire mountain range gone, replaced permanently by a waterway that didn't exist 6 years earlier, and that could, in theory, change the balance of global oil trade forever. Think about what that actually means for a moment, because it's easy to let a number like 400 million cubic meters slide past without truly absorbing it. If you loaded every single cubic meter of that displaced rock onto standard dump trucks and lined them up bumper to bumper, the convoy would stretch far enough to circle the earth several times over, a physical monument to 6 years of relentless, unglamorous labor carried out by people whose names will likely never appear in a headline, and the stakes behind that labor were never abstract. Every single day this canal sat unfinished, roughly 20 million barrels of oil kept funneling through a single vulnerable choke point that any regional conflict, any accident, any deliberate blockade could shut down in an instant, sending fuel prices spiking for billions of people who have never even heard of the Strait of Hormuz and never will. That's the quiet, unglamorous truth behind almost every megaproject like this one. Nobody wakes up one morning and simply decides to remove a mountain range for fun. They do it because the alternative, permanent vulnerability, permanent dependence on a single fragile gap of water controlled by forces nobody can fully predict, is simply unacceptable at the scale modern economies now operate. Engineers involved in the project have been careful to point out that the canal doesn't eliminate risk entirely, it redistributes it, shifting global shipping routes toward a corridor that, at least on paper, is easier to defend, easier to monitor, and far harder to blockade than a narrow natural strait squeezed between two coastlines. Whether that theory holds up under real geopolitical pressure is something only time, and perhaps a future crisis, will ultimately reveal. What's undeniable, though, is the sheer physical audacity of what was actually built here. A canal deep enough to swallow a 50-story building, wide enough for the largest supertankers on Earth to pass safely in both directions at once, and long enough to cut clean through a mountain range that geologists once considered functionally impossible to tunnel through using any method available at the time. Consider, too, the sheer logistics of simply keeping 10,000 people alive and working in one of the most remote, inhospitable corners of the Arabian Peninsula for 6 consecutive years, feeding them, housing them, treating their injuries, replacing their equipment, all while a 4,000-page blast plan ticked forward one detonation at a time with almost mechanical precision. Workers who spent years living inside that construction camp describe a strange, almost surreal rhythm to life out there, waking before sunrise to the low rumble of trucks already moving, watching the mountain visibly shrink week after week, month after month, until eventually the landscape they'd first arrived to survey simply didn't exist anymore, replaced by smooth concrete walls and navigation lights blinking in the dark. There's something almost poetic about that transformation, watching raw, ancient stone that had stood untouched for millions of years get reshaped piece by piece into a corridor built specifically to move the modern world's most valuable resource just a little bit safer, a little bit faster, and a little bit further out of reach of any single point of failure. And now that the last worker has walked off site, now that the cranes are gone and the temporary jetties have been dismantled, what remains is something almost eerily quiet compared to the 6 years of controlled chaos that built it, just water, moving steadily between two seas through a channel that, until recently, was solid mountain. Somewhere out past the breakwaters right now, a supertanker the size of several football fields is likely gliding through those 3 lock systems, rising 650 meters above sea level and descending again on the other side, completely unaware, in a sense, that it's making history simply by existing in that specific place at that specific moment. This was, for now, just a conceptual vision brought vividly to life, like share and subscribe for more.